In my previous video, I went over a detailed method for beginners on how to draw pretty much any Lewis structure. So I'm going to work through these examples using that method. I'm not going to go as detailed as I did with the previous video, of course, because I just kind of went over that. But I am going to explain as I go through all of these structures, and I'm sure you'll have seen at least probably some of these on your exams when they come up. Okay, so let's begin. So we're going to start easy and kind of work our way to maybe more complex, if you will. So we'll start with N2. And with step one, we want to connect the atoms. So it's easy because there's just two atoms here. So we connect them with a line. A line represents 2 electrons. Now we need to count the number of electrons. We got to add the electrons. And nitrogen, if we look on our periodic table, nitrogen is here. And if we start from the left and count, 1, 2, 3, 4, 5, nitrogen has 5 electrons, 5 valence electrons. Since there's 2 of them, we need to add 10 electrons. Now there's 2 in a bond, so we need 8 more. So we'll put 4 on each side. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we added our electrons. The next step is to add the charges, and the expected equals the owned. So we expect there to be 5 electrons. I'm going to write this down. Charge equals expected minus owned. We're going to use these same equations, this same equation all the way through. This process never changes. It's going to be super redundant, and you're going to be awesome on the exam because you'll know the method. So the charge equals the expected minus the owned. Well, the expected number of valence electrons is we get from the periodic table, count from the left. So we expect there to be 5 for nitrogen. So 5, how many are owned in this structure? How many does it own? Well, here we have 1, 2, 3, because 2 electrons in a bond, and each 1 electron is owned by this nitrogen, the other electrons owned by this nitrogen. So 1, 2, 3, 4, 5. So this one has 5, this one has 5. Since the expected equals the owned, there's no charge. And now our last step is the central atom. And for carbon or nitrogen as central atoms, we want them to obey the octet rule. Here, we don't obey the octet rule because there's only 6 electrons associated with this nitrogen, and same with the other one. There needs to be 8. So to do that, what we're going to do is move electrons. We're going to take these 2 electrons down here and move them in to make a bond, make a double bond here. So now we have 4 electrons here. Now, this nitrogen, 2, 4, 6, 8, this nitrogen obeys the octet rule, but this one doesn't obey the octet rule. See this? This still only has 6 around it. So we didn't change the number of electrons around this nitrogen, but we did around this one. This has 2, 4, so this obeys the octet rule, this one doesn't. So we're going to take these 2 electrons and make a triple bond. Let's make these look better. And by doing that, we now have obeyed the octet rule with each nitrogen. We have 2, 4, 6 electrons in these bonds, plus these 2 here. So there's 8 for this nitrogen and then 8 for this nitrogen. It's obeyed the octet rule, and we're happy. We want to double check the charges. There are how many owned electrons on this nitrogen? 1, 2, and then 1 from each bond. There's 5. So the 5 owned on each side. So the expected equals the owned. So we're done. Now we'll probably put these electrons on the side right here, just to make it look nice. Okay, now for O2, I'm going to go through these a little more quicker because we just did N2 in detail. Step 1, we'll attach the atoms. Step 2, we'll add the electrons. Oxygen's here, we count from the left. 1, 2, 3, 4, 5, 6. So 6 electrons per oxygen. That means we need 12 electrons total. There's 2 in the bond. 3, 4, 5, 6, 7, 8. We add them to make octets. So this has 8 electrons around it, so we're good. We can move to the next one. 9, 10, 11, 12. We added our electrons. Now we look at the charges, and the charge on this oxygen, so the expected is 6, and this one, the owned is 1, 2, 3, 4, 5, 6. The owned is 7. So for this oxygen, we have 6, which is expected, minus 7 is owned, so the charge is -1. And then this one, 1, 2, 3, 4, 5. So its charge is +1. So just like before in the previous video, we want to complete octets. So this one doesn't have a complete octet. it needs electrons. It's going to get the electrons from this one. So we'll take these 2 electrons and make a double bond. And when we do that, we recount what our charges might be. 1, 2, 3, 4, 5, 6. There's 6 owned electrons here. 1, 2, 3, 4, 5, 6. 6 owned electrons here. So the owned equals the expected, so there's no charge. So this is our Lewis structure. Now this isn't the correct structure of O2, but anyways, this is what Lewis structure predicts in this theory, even though it's not correct. It's the Lewis structure. Okay, so Br2, same thing, we attach the atoms. So Br is attached to Br. Whoops. And now we need to add the electrons. We go to bromine. Start from the left. 1, 2, 3. Oops, skip the transition metals. 1, 2, 3, 4, 5, 6, 7. So there's 7 electrons, valence electrons. We need to add, there's 2 bromines, so there's 14 electrons total to add. 2 in the bond. 3, 4, 5, 6, 7, 8. We now have an octet here. 9, 10, 11, 12, 13, 14. We now have an octet here. Now we check out what the charges are be, expected minus the owned. Well, we expect bromine to have 7 based on our periodic table. How many electrons does it own? 1, 2, 3, 4, 5, 6. It owns 6 non-bonding electrons. And then in a bond is comprised of 2 electrons. So one is owned by this bromine, the other one's owned by this bromine. So this bromine has 7 owned electrons. It's not charged, neither is this one. So since there's no charge, we check to see if there's an octet. 2, 4, 6, 8. There's 8 electrons associated with this bromine. Same with this one, there's 8 electrons. So we're done. We don't have to make any double bonds or triple bonds or anything like that. That's our structure. Okay, so we'll move along, CO. And we have step 1, we attach the atoms, carbon to the oxygen. Step 2, we add the number of electrons. Here's carbon, come from the left, 1, 2, 3, 4. There's 4 electrons from carbon, and then O for oxygen, there's 6 if we count from the left. So the total number of electrons is 10 electrons, 6 plus 4, simple math. There's 2 in this bond here. And now we want to add electrons. Now we generally want to start with the central atom. And here there's not really a central atom, but if given the choice, we start with the one that's the most electronegative. So the one that's furthest to the right on the periodic table. Oxygen's furthest to the right, so it's the greater electron hog. So we're going to put these electrons around the oxygen first to form an octet. So there's 2, 3, 4, 5, 6, 7, 8. Now has formed an octet. We need to add 2 more. So we'll add those 2 remaining ones to the carbon right here. Now the next step, we need to add the charges. Expected, the charge equals the expected minus the owned. For carbon, we expect there to be 4. And it currently owns 3 because there's 1 electron in each bond. 1 electron is owned by the carbon. The other electron in this bond is owned by the oxygen. So this has a charge of +1. And then oxygen, we expect it to have 6 from our periodic table. How many does it own? 1, 2, 3, 4, 5, 6, 7. It owns 7, so its charge is -1. So what we'll do, and see, carbon doesn't have a complete octet, so it needs electrons, and it's going to get those electrons from oxygen. So oxygen, I'm going to delete those and put them here as a shared bond between them. Now in this way, if we look at it, 1, 2, 3, 4, carbon is no longer charged, right? Because we expect it to be 4. Now there's 4 owned, 1, 2, and then 1 in each bond. So that's 0. So that's good. And oxygen is now 0, 1, 2, 3, 4, 5, 6. So there's no charge. So that might seem okay because we've gotten rid of all the charge, but carbon doesn't have a complete octet. And that's like one of the most important rules. That's right at the end, the central atom. We need to ensure that we obey the octet rule for the central atoms. And carbon always has to obey the octet rule. In terms of the octet rule, there's only 6 around this carbon. 1, 2, and then 2 in each bond. So 4, 5, 6 here. It needs to be 8. So we need more electrons, even though we're not charged. So we'll take those 2 electrons from oxygen there, and we'll put those 2 electrons to create another bond a triple bond. And now carbon has a complete octet. There's 6 electrons in the 3 bonds, plus these 2 here makes 8, and then the same for oxygen. I'm going to move these electrons over here just so it kind of looks a little nicer. But since we moved electrons around, we got to recalculate the charge. So carbon has 4 expected, right, from the periodic table. Carbon's here, 1, 2, 3, 4. How many does it own? 1 from each bond, so there's 3 plus another 2. It owns 5, so its charge is -1. And oxygen here, we expect it to have 6 based on the periodic table. It owns 1, 2, 3. It owns 5, so its charge is +1. And this is very odd for the most electronegative atom to have a positive charge on it, but this is required in order for the octet rule to be obeyed. So this is our Lewis structure here. Awesome. Isn't this method sweet? It works. Like even when we see like anomalies and exceptions, there's no exceptions. It works for what you're going to see in general chemistry. Okay, so step 1, C in the N. We attach the atoms. Step 2, we add the electrons. Carbon, we count from the left. 1, 2, 3, 4. So there's 4 electrons. Nitrogen is 5 here, right beside carbon. 1, 2, 3, 4, 5. So there's 4. We expect 4 valence electrons for the carbon, plus 5 for the nitrogen. That's what it would be expected. And if each atom has this many electrons, there'd be no charge. But since this thing is charged, it has a negative charge, that means it has more electrons than expected. 1 more, because oxygens are negative. So this is 10. 5 plus 1 is 6, but we need a 4 there. That's 10. So 10 electrons around this. Now we have 2 in the bond. And again, we're going to start with nitrogen because it's further to the right. This would serve as our central atom. If we had a central atom, it's the least electronegative, furthest to the left. So we'll put electrons first on the nitrogen to form an octet. There's 2 here in the bond, 3, 4, 5, 6, 7, 8. We now have a complete octet. So we'll add the other 2 to carbon right there. Step 2 is we'll determine the charge. Carbon, we expect there to be 4. There's 3 owned electrons, 1 from the bond, and these 2. So currently its charge is +1 here. And nitrogen, 1, 2, 3, 4, 5, 6, 7. It has 7 owned electrons. We expect there to be 5, so 5 minus 7, expected minus owned, is -2. -2, okay. Now we need 2 complete octets. Nitrogen has a complete octet, but this carbon doesn't. See, there's only 4 electrons around this carbon. So it needs more electrons. It's going to grab those from nitrogen. So I'm going to take these 2 right here and make a double bond. Get rid of our charges here. And how does this look? Well, carbon still doesn't have a complete octet. So you know what? Before I calculate charges again, I know that carbon has 2, 4, 6 electrons around it. It needs 8 to complete an octet. It needs more, so it's going to grab 2 more electrons from the nitrogen here. And now we have 6 electrons in the bonds, plus these 2 makes 8, so we have a complete octet for the carbon. And then similar for the nitrogen as well. Just moving these electrons here. Now how are charges, because we moved electrons around? Well, carbon expects to have 4. How many does it own? 1, 2, 3, 4, 5. So we have 5. So its charge is -1. What about the nitrogen? 1, 2, 3, 4, 5. So it's expected to have 5 based on the periodic table. And now we counted 1, 2, 3, 4, 5. So its charge is 0. So the -1 charge goes on the carbon like this. Now there is delocalization you may see. So your prof might prefer you to express it this way, to write the structure in square brackets and then put the -1 here, saying the -1 is partially delocalized throughout the structure here. One thing I'm not covering in this video is resonance structures. This is just doing Lewis structures, straight up Lewis structures. That's it, hardcore, but no resonance structures. If you want those, let me know. I can make a video on that. Okay, so we'll do NO, nitrogen and oxygen. Step 1, we attach the atoms. Step 2, we got to add the electrons. So nitrogen and oxygen. Nitrogen's here, count from the left, we go 5, and oxygen has 6. So that's 5 plus 6, so there's 11 electrons to add. There's, oh, it's an odd number. That's cool. There's 2 here. Now we need to add them starting with the oxygen because it's furthest to the right. This is, nitrogen would be a central atom if there were more atoms around here. And we add electrons to the outer atoms first, the more electronegative atoms. So there's 2, 3, 4, 5, 6, 7, 8. 7, 8. We now have a complete octet. So we'll put the rest on here. 9, 10, 11. Okay. Now we look at our charges. So we expect there to be 5 electrons owned by nitrogen, but it actually owns 1, 2, 4. So its charge is plus 1. Oxygen, 1, 2, 3, 4, 5, 6, 7. It owns 7. We expect there to be 6 based on the periodic table. Minus 7, so its charge is negative 1. And 1, 2, 3, yeah, okay. Now, do we have a complete octet? Well, we do for oxygen, but not for nitrogen. And so it actually needs more electrons. Now, we might run into problems here, but because it's an odd number, but that's okay. So since we want to try and create an octet, we'll move these 2 electrons here. So we'll make those there and then we'll get rid of them. So we move them to make a double bond. Nitrogen now has 1, 2, 3, 4, 5, 6, 7 electrons around it. And oxygen has oxygen has a complete octet. Now, what if, so since we only have 7, I'm going to get rid of these charges because we move some electrons, so we're going to have to recalculate the charge. But let's say we move 2 more electrons here because we want to complete an octet. And let's say we make a triple bond by moving these 2 electrons here, just like down here. And then we have something like this. Is this possible? Well, nitrogen now has 2, 4, 6, 8, has 9 electrons around it. 9 electrons in its valence shell. It violates the octet rule, like exceeds the octet rule, which is not allowed. So we can't do that, unfortunately. So we can't get a complete octet for both nitrogen and oxygen. This is the best we can do because we have an odd number. So this is our Lewis structure here. Okay, ClO minus, we'll connect the atoms, and then we'll add the electrons. We'll look at chlorine. Chlorine is right here. And start from the left, 1, 2, 3, 4, 5, 6, 7. So chlorine has 7 valence electrons. So this one has 7. Oxygen has 6 as before, if we count from the left, plus 1 for the charge, because it has 1 more electron than expected. That's why it's negatively charged. And there's 14 electrons, 2 in the bond. And we'll start with, doesn't matter which one we'll start with, but we should start with the oxygen since it's the more electronegative atom. 1, 2, oh, there's 2 in the bond. So 3, 4, 5, 6, 7, 8. We have a complete octet. 9, 10, 11, 12, 13, 14. Okay, now we look at the charge. The expected minus the owned is our charge, and we expect there to be 7 electrons on chlorine based on our periodic table. How many does it own? Well, it owns 1 from the bond because there's 2 electrons in this bond. 1 is owned by the chlorine, the other is owned by the oxygen. 1, 2, 3, 4, 5, 6, 7. So it owns 7. We expect there to be 7. There's no charge. What about the oxygen? Charge equals expected minus the owned. We expect there to be 6 electrons based on the periodic table. So here's oxygen. 1, 2, 3, 4, 5, 6. But it owns 1, 2, 3, 4, 5, 6. It owns 6 plus 1 in the bond, 7. So 6 minus 7, negative 1. So it's negatively charged. And this is our Lewis structure here. Or your prof might like to see you write it in square brackets. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Like this. And putting the charge up here. So like negative 1, saying that this negative is shared between these 2 atoms. Alrighty, next set, beryllium hydride. So we have beryllium as the central atom. It's written to the left. in the periodic table, it's now further to the left. In terms of like where it would be for electronegativity, hydrogen fits right here, but hydrogen always loses. It's always an outer atom and it only forms one bond. This is written to the left here, beryllium. It's less electronegative and it's singular, so it fits the bill. And then we'll attach the atoms, put hydrogen on both sides there. Now we need to add the number of electrons. Beryllium, we start from the left. 1, 2, has 2 valence electrons. 2, hydrogen has 1 each, so 1 times 2. So there's 4 electrons to add. And look at that, there's 2 electrons in each bond. We have all 4 electrons here. This is our Lewis structure. No need to go further. Okay, CS2. Carbon is the central atom. It's singular, it's written to the left here on the periodic table. Carbon is more to the left than sulfur, so it's less electronegative. So we'll attach all the atoms to the central atom. Now we want to add the number of electrons. Carbon has 4. Right, if we go on a periodic table, count from the left, 1, 2, 3, 4. It has 4, plus sulfur has 6. Sulfur is right here, count from the left, 1, 2. We always skip the transition metals, 3, 4, 5, 6. So there's 6, and there's 2 of them, 12, 13, 16. So there's 16 electrons to add. There's 4 in the bonds, and we add them to the outer atoms first to form octets. So 5, 6, 7, 8, 9, 10. This now has a complete octet. There's 8 around the sulfur because 2 electrons per bond. 11, 12, 13, 14, 15, 16. So we now have 16 electrons in here. Next step is to check the charge. And sulfur has 1, 2, 3, 4, 5, 6. It has 7 owned electrons, 1 from each bond. We expect there to be 6. Right? The charge equals the expected minus the owned number of electrons. Well, we expect sulfur to have 6 based on the periodic table. It owns 7, 1, 2, 3, 4, 5, 6, and then 1 in the bond. So its charge here is -1. That would be the same for this sulfur here. This would be -1. And what about the carbon? Well, we expect carbon to have 4 based on the periodic table. It owns 2, 1 from each bond, 4 minus 2. So its charge is +2. So carbon doesn't have a complete octet, right? And the next step is that the central atom must complete an octet if it's carbon or nitrogen. So it only has 4 in its associated with it, 4 in its valence shell. So therefore, it needs to grab electrons from somewhere. It's going to grab electrons from these atoms, these negatively charged atoms. So since these have an excess amount of charge, we'll take these 2 electrons and make a double bond. I'll just delete these here. And at this point, carbon still doesn't have enough electrons to fulfill the octet rule. There's only 6 around this carbon, 2 electrons at each bond. So it needs 2 more electrons. It's going to grab it from this sulfur because this sulfur has an excess amount of electrons. It's negatively charged. So take away 2 of them here and make a double bond. And let's check it out. Carbon has an octet now. There's 8 electrons, 2 in each bond around it. Each sulfur has a complete octet because there's 4 non-bonding and then 4 bonding electrons associated with this sulfur. So they all have complete octets. And the expected minus the owned is going to be good for all of them. Sulfur we expect to have 6. It owns 1, 2, 3, 4, then 1 in each bond, 5, 6. So its charge is 0. And then carbon, we expect there to be 4. It owns 1 electron in each bond, so 4 electrons. 4 minus 4, it's not charged. This is our Lewis structure here. For these next set of ones, we have chlorine and oxygen. So chlorine's the central atom. It's written furthest to the left. It's singular. If we look at our periodic table, chlorine's here and oxygen is here. So it's further down, which could make it a central atom. It is further to the right. But unfortunately, this oxygen is much more electronegative. It's almost never a central atom. unless it's kind of singular and you're bonded to fluorine, or there's, say, 2 chlorines or something like that. But anyways, we have chlorine as the central atom. It's written to the left is singular, and it's less electronegative, so we'll write it like that. Next, we'll add the electrons. Chlorine has 7 electrons to add, valence electrons. Here's chlorine here. If we start from the left, 1, 2, 3, 4, 5, 6, 7, we get to 7. And oxygen, if we start from the left, 1, 2, 3, 4, 5, 6, we count 6. So chlorine has 7 expected electrons, oxygen has 6 expected electrons, and there's 2 oxygens. So there is, let's see, 12, 19 electrons. You know what? I think, yeah, this is fine. I think this should have been negatively charged here. I'm gonna put a negative charge. Just whoops. I'm gonna make this negatively charged. There is ClO2 that's not negatively charged, but just you probably won't see it as commonly as you will ClO2 minus chlorite. You'll probably see this. So I'm gonna change the electrons. We're gonna add an electron because of this. We'll make it negatively charged, which means it has 1 more than expected. So we're going to add 1 there. So I'll say there's 20 electrons here, 12, 13. Okay. So we have 4 in the bonds, 2 from each bond, and we need another 16. And we're going to add them first to the outer atoms to complete octets. So here there's 1, 2, 3, 4, 5, 6, 7, 8. We have a complete octet. And 9, 10, 11, 12, 13, 14. 15, 16 in these 2 bonds. So we have 16 total. Now we have a complete octet in both of the outer atoms. So we have to add the remaining electrons to the central atom. So 16, 17, 18, 19, 20. Okay, next step is we need to determine the charge. Oxygen has an expected number of 6 electrons. We expect there to be 6 electrons. Minus how many does it own? Well, 1, 2, 3, 4, it owns 6, plus 1 electron in this bond. So this bond is made up of 2 electrons. 1 is owned by the oxygen, the other is owned by the chlorine. So the oxygen owns 7. The expected minus the owned equals the charge. So this has a charge of -1. This one would be charged of -1. What about chlorine? Well, we expect there to be 7 based on the periodic table. It owns 1 in each bond, so 2, 3, 4, 5, 6. It owns 6. So its charge is +1. Okay, so now we have a central atom that's not carbon or nitrogen. So what we want to do is we want the expected to equal the owned electrons if possible. Right? So we don't want there to be a charge. We expect there to be 7, but now currently it owns 6. So it needs an extra electron. So it's going to grab one from one of these oxygens. Doesn't matter which one. I'll choose this one here. And we'll take 2 electrons, and we're going to move them down here to create a bond. So whenever we move them, we're always moving them to make double or triple bonds. And by doing this, just erase this here, we now have the expected equals the owned for this chlorine. We expect there to be 7. It now owns 1, 2, 3, 4, and then 1 in each bond, which is 7. Which is 0, and then this oxygen is no longer no longer charged. We expect there to be 6 in this oxygen. It owns 1, 2, 3, 4, and then 1 in each bond, 5, 6. So 6 minus 6 is 0, so it's not charged. And actually, I'll put the electrons here just so it kind of looks a little bit nicer. And this is our Lewis structure here in all its glory. Now, if you see a structure with a charge, your prof may want you to draw it in square brackets, and especially if you're doing resonance structures. This has a resonance structure, which we're not covering in this video. I'll just do negative, not -1, doesn't matter. This indicates that the negative charge is shared throughout the whole molecule. It's really mostly just on these 2 oxygens here. Okay, N2O. So our first step is to connect the atoms. Now, how are we going to connect these atoms? Is O central? It is singular, but it's written to the right in the molecular formula. And on our periodic table, it is to the right of nitrogen here. And oxygen is more electronegative than nitrogen. So we're not going to have oxygen as the central atom. That means we only have one choice. We have to bond the 2 nitrogens together and then bond the oxygen. Well, we have a couple choices. We could have made a triangle here, but we'll make it a line here. In general chemistry, when you're starting off learning these things, you're usually not given structures like that unless you're given kind of more information. So we're going to have one nitrogen as a central atom, and the other two are going to be outer atoms. And we're just literally following the same method. So we want to count the number of electrons. Nitrogen has 5. Here's nitrogen, count from the left. 1, 2, 3, 4, 5. It has 5. So there's 5 valence electrons. 5, there's 2 of them. And oxygen has 6. Here's oxygen, count from the left. 1, 2, 3, 4, 5, 6. So plus 6 equals 16. So we need 16 electrons. We have 4 in the bonds. We need another 12. We're going to start adding electrons to oxygen because it's more electronegative. It's further to the right, so it's a greater electron hog. It has more electron muscle. So we're going to add 6 electrons here so that this now has a complete octet. 2, 4, 6, and then 2 in the bond is 8. 4, 6, 8. So we have 10 electrons total. We need another 6. We'll add them around to the nitrogen to form a complete octet. And that's it. I think we got our 16 electrons on here. Next step is we want to calculate the charge. So we expect nitrogen, we'll do this nitrogen first, we expect it to have 5. Charge equals the expected minus the owned. We expect it to have 5 based on the periodic table. How many electrons does it own? 2. It owns 6 non-bonding, and then 1 electron in the bond. See, this bond is comprised of 2 electrons. 1 electron is owned by this nitrogen. The other electron is owned by the other nitrogen. You could think of the line as like this too. A line is just kind of more commonplace to see. So this nitrogen owns 1, 2, 3, 4, 5, 6, 7. So its charge is -2. The way we've written it, I'm going to put this back to lines because I like it better. This nitrogen has a charge of, well, we expect 5 based on the periodic table. It only owns 2, 1 from each bond. So it's +3. So +3. And then this oxygen, we expect there to be 6, but it owns 1, 2, 3, 4, 5, 6, and then 1 in the bond, 7. So its charge is -1 as it's written. Yeah, I'll erase this here. So now what we want to do is we want to look at the central atom. And for central atoms that are carbon or nitrogen, we want these to obey the octet rule. That's the most important thing. Right now, in terms of the octet rule, we only have 4 electrons associated with this carbon, 2 in each bond. Not owned electrons, but just in its valence shell. It's associated with this nitrogen here. There's 4, so it needs another 4 more to complete octets. Let's grab one or a set from this nitrogen here. So we're going to take these 2 electrons, form a double bond, and I'm going to erase these charges here. Now there's 6 electrons associated with this nitrogen here. We need another set. Now, are we going to take electrons from the oxygen or from the nitrogen? And if it could go both ways, but I would take it from the nitrogen. We need 2 more electrons to fulfill the octet here. I just took these 2 electrons and moved them here to make a bond, because we're always making double or triple bonds when we move these electrons, because oxygen is more electronegative. It's going to be more of an electron hog. So if anybody's going to be negative, it's going to be oxygen predominantly. Okay, so in this case, now we have a complete octet. If we look at this nitrogen here, it has an octet, 2 and then 6 from the bonds, so that's 8 for this nitrogen. Same thing with this middle nitrogen. It has 4 bonds, which means it has 8 electrons associated with it for the octet rule, 8 valence electrons. So the octet rule is satisfied. Same thing with this oxygen that we've already looked at. We didn't do anything with it. What about the charges? Well, expected minus owned is what the charge is. We expect this nitrogen to have 5 based on the periodic table. It owns 1, 2, and then 1 from each bond. It owns 5, so it's not charged. So that's cool. And what about this nitrogen? We expect there to be 5. It owns 1 from each bond, 1, 2, 3, 4. It owns 4. So its charge is +1 here. So this is a valid Lewis structure. Totally good. You may Your prof may want you to write it with square brackets like this. Oh, yeah, might write it like this. Just you kind of get rid of the charge. I like kind of writing it this way, but they may have this desired. It shows that there's no charge overall. Now remember last time when we were at this situation, get rid of this, where we had the double bond here, and we decided, not the double bond, the 2 electrons here, and we took electrons to make this triple bond. Well, we could have taken electrons from the oxygen. I'm going to put this back here. And if we did that, and you could try it yourself, we would end up with something like this. And if we looked at the charge, and if we looked at what the charge would be, this nitrogen has 1, 2, 3, 4, 5, has 6 owned. We expect there to be 5. It owns 6 right now, so its charge is -1. This nitrogen still has a charge of +1 because it has 4 bonds, just like this one has 4 bonds. And this oxygen now is no longer charged because we expect there to be 6. It owns 1, 2, 3, 4, and 1 in each bond, 5, 6. So this is also a valid Lewis structure as well. Both of them may get you full marks on your exam, but you may need to know which one is the preferred structure, and it's absolutely going to be this one up here because we have the negative charge on the more electronegative atom. Moving along, NO2 will connect the atoms. The nitrogen is central because it's singular. It's written to the left. On the periodic table, it's further to the left than oxygen there. And now we want to count the number of electrons. Nitrogen has 5 electrons. If we start from the left and count to nitrogen, 1, 2, 3, 4, 5. And oxygen has 6. If we do that same thing, count from the left, there's 2 oxygens, so times 2. So this would be and 12, 17, 12, yeah, 17 here. Okay, and now there's 4 here, and we're going to start adding them to the outer atoms to form octets. So 4, 5, 6, 7, 8, 9, 10 electrons total. This now has a complete octet because there's 8 electrons around it, 2 electrons in each bond. 2, 4, 6, 8, 10. So we need 7 more. 1, 2, 3, 4, 5, 6. We have a complete octet here as well, where we need 1 more electron. So we're going to put it on the nitrogen because we won't exceed octets with these outer atoms here. Next, we'll calculate the charges. The charge equals the expected minus the owned. Based on the periodic table, we expect oxygen to have 6. Minus how many does it own? It owns 1, 2, 3, 4, 5, 6, and then 1 in the bond. See, there's 2 electrons here. 1 is owned by oxygen. The other one's owned by nitrogen. So 6 minus 7. So this has a charge of -1. Same thing with this oxygen here. This nitrogen charge is, we calculate it, we expect there to be 5 based on the periodic table. It owns 1 from each bond, so that's 2 plus this one here, 3. So that's +2. So that's +2. I'm just going to delete this here to clean things up. Now we want nitrogen to complete its octet. Now this is an odd number, so we want the central atom to have a complete octet because it's nitrogen. If it's carbon or nitrogen, we want it to complete an octet. Otherwise, we want the expected to equal the own number of electrons. So in terms of the octet rule, we haven't done that yet for nitrogen. It doesn't have a complete octet. It only has 5 electrons associated with it. 2 in each bond plus this one single one here. So we're going to grab some electrons from oxygen. We'll move these 2 over. And when we move electrons, we make double bonds so these 2 electrons that were here are now in a bond. That's what the line represents, 2 electrons. And we still don't have a complete octet, do we? We have 2, 4, 6, we have 7 right here. So let's get rid of this charge. Let's move another 2 over, and let's see what happens there. So if we take 2 electrons, I took 2 from this oxygen to make a double bond between here. And if you look at it this way, this oxygen has a complete octet. 1, 2, 3, 4, and then 1 electron in each bond, 5, 6. So it's owned equals the expected. It's not charged. Same thing with this one. But this nitrogen we've exceeded the octet rule with this nitrogen, and we can't do that. We can't do that with carbon and nitrogen. So there's 2 electrons in each bond. There's 8 electrons around this nitrogen bonding electrons plus this one. So there's 9, which means we violated the octet rule. We can't do that. So I'm going to take the 2 electrons in this bond here. I'm going to put it back on the oxygen. I'm going to put the charge back here to -1. And this nitrogen now has a charge of +1. We expect there to be 5. It owns 1 from each bond. That's 3 plus 1 here, 4. So 1. So +1. So this is as far as we can go with our NO2. There's a lone electron here, a radical. It's a non-bonding electron, but that's the best we can do. We could put the negative on this one. This one could have been a single bond, and there is resonance structures here, if you've covered that, but we're not covering resonance in this video. Your prof may want you to write it in square brackets, like this. This just indicates that, yeah, normally we'd put the charge here, but if there's no charge, we could potentially write it there, and then you'd have to kind of add it up. But this way tells you where the charges are. Okay, so NO2 minus, okay, here's nitrite. It's the same as NO2, but now it's negatively charged. So that means it has 1 extra electron. So there's 18 electrons in this NO2. So just like before, we're going to do the exact same thing. We'll make it the central atom. We'll add 18 electrons. There's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this electron now has a buddy here, and we're going to create octets. We need to create an octet with this nitrogen, so we'll make a double bond here. In this case, now, this oxygen has a complete octet. See, there's 4 electrons here, and then 4 in the bonds, so this has a complete octet. This one has a complete octet. And this nitrogen has a complete octet. There's 6 electrons in its bonds and 2 non-bonding electrons, so that's 8. So that's great. So this is negatively charged. And in terms of the charge, the expected equals the owned. For this oxygen, we expect there to be 6 based on the periodic table. It owns 6, 1, 2, 3, 4, and then 1 from each bond. So its charge is 0. And then same thing, charge is going to be 0 on nitrogen here. The periodic table tells us we expect there to be 5. It owns 1 from each bond. That's 3, 4, 5. 5 minus 5, so 0. So this is our Lewis structure here. You could write the negative on the other side, or you could write it like this. O, double bond, N, O, O, and put the -1 here, showing that this -1 is delocalized or spread out throughout the nitrogen, predominantly on the negative, on the oxygens. Okay, moving along, NOCl. Now, N is furthest to the left of oxygen and chlorine, and it's singular. It's written to the left here as well. It's the least electronegatives, so it's it's going to be the central atom. So we'll have nitrogen bonded to oxygen and chlorine. Now we need to add the correct number of electrons. If we go on NOCl, if we go from the left for nitrogen, we count 5 to get to nitrogen. 1, 2, 3, 4, 5. So we expect it to have 5. Oxygen is just 1 more is 6. And then chlorine, its expected valence electrons is 7. We start at the left. 1, 2, 3, 4, 5, 6, 7. So we have 5 plus 6 plus 7. And if we add those up, that's 18. And we're going to add those. First, I'll add them to oxygen because it's more electronegative. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We now have a complete octet with oxygen. 11, 12, 13, 14, 15, 16. We now have a complete octet with chlorine, 6 plus these 2 bonding electrons. So we need to add 2 more. We'll add them to the nitrogen like that. Okay. Now, our next step is we will add the charges, and the charge equals the expected minus the owned. We expect chlorine to have 7 electrons, 7 valence electrons, which we got here from the periodic table. How many does it own? It owns 6 plus 1 from the bond. right? This bond is made up of 2 electrons. 1 electron in this bond is owned by the chlorine, the other one's owned by the nitrogen. And this is kind of fanciful thinking. It's more like housekeeping for us. 2, 3, 4, 5, 6, 7. So it's not charged. For the nitrogen, we expect there to be 5 based on the periodic table. It owns these 2, and then 1 from each bond. 3, 4, it owns 4. So its charge is +1, the way we've written it. And then oxygen, we expect there to be 6. It owns 1, 2, 3, 4, 5, 6, 7. 1 from this bond here. It owns 7, so its charge is -1. And, okay, now we want to see, have we completed octets? Well, I'm going to clean this up here. We need to complete an octet for the central atom because it's nitrogen. Nitrogen and carbon, we always want to have a complete octet for the central atom. That's key. That's the last step. Well, we don't have a complete octet here. There's only 6 electrons associated with this nitrogen, 4 bonding electrons and 2 non-bonding electrons. So it needs more electrons. And it's not going to grab those electrons from chlorine because chlorine isn't charged. It doesn't have an excess number of electrons. Oxygen does. It has 1 more electron than what's expected. So this has an excess amount of electrons. This is deficient in electrons. You can tell that it's because it's positive charge. So we're going to take these 2 electrons and move them to make a double bond. And by doing that, we now have a complete octet for nitrogen. See, there's 6 from the bonds and 2 from the non-bonds. We have a complete octet. We have a complete octet for oxygen still. There's 4 here and then 4 from the bonds. So this is our Lewis structure right here. And we're not charged either. I'm going to move these electrons just so it looks a little nicer. This one we know is not charged. Nitrogen, we can recalculate. The charge equals the expected minus the owned. We expect there to be 5. It owns 1 from the bond, 2, 3, and then these 2, 1 from each bond, 5. So 5 minus 5, that's 0. And then oxygen, we expect there to be 6. It owns 1, 2, 3, 4, and then 1 from each bond, 6. So it's not charged as well. Okay, so this next one here, another rule, if it starts with an H, then the H goes to an O. Now there is a structure where the H can go to the end, but generally, in general chemistry, you're pretty much always going to see the H. If it starts with an H, it's bonded to an O. So nitrogen is our central atom, and the outer atoms are oxygen, and the H is bonded to an O. If there's 2 H's, 1 H to each O, 3 H's, blah, blah, blah. Okay, so now we're going to add up all the electrons. Hydrogen has 1 electron. We start from the left, we get to hydrogen, that's 1. Nitrogen, we start from the left, we count 2, 3, 4, 5, we get to nitrogen. Count 1 more, 6 from the left, we get to oxygen. So there's 1 for hydrogen, 5 for nitrogen, plus 6 for oxygen, times 2, because there's 2 oxygens. This is 18, I think, 12, 13. Yep, 18 electrons. And we're going to add them first to the outer atoms to form octets. There's 2 electrons here. So if we add 6 more, 3, 4, 5, 6, this oxygen now has a complete octet, 2 bonding and 6 non-bonding. Now we'll add them to the other outer atom. Remember, nitrogen is our central atom, so we add electrons to it last if there's any left over. This oxygen has 4 around it, so we need to add another 4 to complete an octet. How many electrons do we have total? 2, 4, 6, and another 6. We have 12, so we need to add 6 more. 1, 2, 3, 4. We can only add 4 to this oxygen, right? Because we can't exceed an octet. There's 4 bonding and 4 non-bonding, so this has a complete octet. So we can't add any more electrons to oxygen, and we can never add more electrons to hydrogen. It can only have this 1 owned electron or 2 total electrons associated with it. So we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. We add 2 more. We have to add 2 more to go. So lastly, we'll add them to the central atom. Next, we'll calculate the charge, which is the expected minus the owned. We expect oxygen to have 6 electrons based on the periodic table. It owns 1, 2, 3, 4, 5, 6, and then 1 from the bond, 7. 6 minus 7, so -1. So this is negative charge of -1. This nitrogen, we expect there to be 5 based on the periodic table. It's 5. It owns 1 from each bond, and then these 2 here, it owns 4. So its charge is +1. And then this oxygen is not charged at all. We expect there to be 6, and it owns 6, 2 non-bonding, and then 1 from each bond is 6. And then same thing with this hydrogen. It owns 1 electron, and we expect there to be 1 as well. Okay, so then our last step is to look at the central atom, and if it's carbon or nitrogen, we want to complete an octet. Otherwise, we want the expected to equal the own. So we only have 6 electrons associated with this nitrogen in its valence shell. So we need more electrons. We're not going to grab it from this oxygen because it's not charged. This one is. So this one has an excess amount of electrons. So we're going to take these 2 electrons and move them over to make a bond. We're now getting rid of these charges here. And I'll get rid of this just to make it a little cleaner. Okay, now this nitrogen has a complete octet. It has 6 electrons from the bonds, and then these 2, which makes 8. Same thing with this oxygen. Its expected equals the owned as well, or it has a complete octet, has 4 non-bonding, plus these 4 bonding from these 2. So this has a complete octet, this has a complete octet. This oxygen is no longer charged. We expect there to be 6 based on the periodic table. It owns 6, 1, 2, 3, 4, and then 1 from each bond. So it's not charged. The nitrogen, we expect there to be 5 based on the periodic table. It owns 5. 1 from each bond is 3, plus these 2 here. It's 5. So this is our Lewis structure here in all its glory. Okay, next we have N3. And there's really only one way to write it unless we write it in a triangle, like in a ring, which we won't do. We'll write it linear, which is how you'll see it in general chemistry. We need to add the correct number of electrons. Nitrogen, if we start in the periodic table from the left and count to nitrogen on that same period. 1, 2, 3, 4, 5. So there's 5 for each nitrogen. There's 3 of them, plus an extra 1, because we have an excess charge. Electrons are negatively charged. If this wasn't charged, then we would have 15 electrons because that's what would be expected, 5 times 3. But we have an extra 1 because it's negatively charged. So we have 16 electrons. We have 4 here. And just like before, we'll follow our method here. 5, 6, 7, 8, 9, 10. We have a complete octet. 11, 12, 13, 14, 15, 16. We have a complete octet. And then we'll do the charge. Charge equals the expected minus the owned. We expect for this nitrogen, we expect it to have 5 electrons. It owns 6 non-bonding plus 1 bonding, so 7. So that's -2. So this has a charge of -2. Similarly, this would have a charge of -2. And this one's going to have a charge of plus. So I'll write it out. So 5, we expect it to be 5. It has 2, so 5 minus 2 is 3. So this nitrogen has a charge of +3. And we want the central atom to have a complete octet, if possible. So we're going to grab electrons from one of these outer atoms. Doesn't matter which one, because they're the same. I'll take these 2 electrons here, and we'll move electrons to make a double bond. That's what we do with electrons. When we say we move them in to make a double or a triple bond. So now those 2 electrons are here. This nitrogen still doesn't have a complete octet because it only has 6 electrons around it, 2 from each bond. So we're going to grab electrons from here. Now the charge is different. I erased the charges. I'll redo the charges in a minute. This has a charge of -1, and then this has a charge of +2 if we were to do the math. Now I can either take the electrons from this nitrogen or from this nitrogen. Either one is actually valid, but I'm going to take them from this one right now, just because this has a greater charge, -2 versus -1. So I'll make a double bond with those electrons there, and this would be -1, this would be +1. So the expected minus the owned gives us these charges here. If we look at this side, this nitrogen, we expect there to be 5. It owns 6, 1, 2, 3, 4, then 1 from each bond, 5, 6. So that's -1, that'd be the same as this one. And then this one owns 4 electrons, 1 from each bond. So 5 minus 4 is plus 1. So this is a valid Lewis structure. Totally valid. If you're to take electrons from this way, you would end up with this 1, 2, 3, 4, 5, 6. And this would be 1, 2, 3, 4 plus 1. This would be negative 2 here. Both of these are valid Lewis structures because we have complete octets with all of the nitrogens. And they're actually resonance structures because they're both valid. And since we can, this negative charge kind of seems like it moves around depending on which structure you prefer. Your prof may prefer you to write the Lewis structure in a square bracket, showing that this negative charge is delocalized throughout. It's kind of spread out throughout here. So you can draw it this way, or you could draw it this way. Either one's valid. Okay, ClF2 minus. So first thing we do is determine which atom is the central atom, and chlorine has to be central atom. It's furthest to the left. It's singular on the periodic table. It's down from fluorine, so atoms that are down and to the left are often less electronegative and the central atoms. So we'll bond everything to the central atom. So that's step 1. Step 2 is we need to count the number of electrons. Chlorine is right here if we count from the left. 1, 2, skip the transition metals. 3, 4, 5, 6, 7. Chlorine has 7. Same thing with fluorine. If we start on the left, we'd count 7 to get to fluorine. So there's 7 for chlorine plus 7 for fluorine, and there's 2 of them, and it's charged. So we need to add an extra electron, right? If this had 7 and then 2 times 7 here, that would be not charged because the expected electrons is of what we add equals how many is what's expected. So, but it's not, we don't have the number of electrons is what we have expected. We actually have 1 more because it's negatively charged, then electrons are negative. So we're going to add 1 more to that, and that's 14, 8, 22, I think. 22 electrons. We're going to add them first to the outer atoms to complete octets. So this fluorine has a complete octet now, 2 from the bond, 3, 4, 5, 6, 7, 8. And then from this side, we'll add another 6. So that's 8 and 8, so we have 16. We have 8 more to add, is that right? 8 more to add to get to fluorine. 1, so 8, 16, 17, 18, 19, 20, 21, 22. 1, 2, 3, 4, 5, 6, 7. Okay, good. So this looks kind of weird, but we're okay. We didn't violate anything. Now the next step is to calculate the charges. And the charge equals the expected minus the own. Fluorine expects to have 7, and it owns 1, 2, 3, 4, 5, 6, and 1 in the bond is 7. So its charge is 0. Same thing with this fluorine. What about this chlorine here? Expected minus the owned. We expect chlorine to have 7 based on our periodic table. It owns 1 from each bond, that's 2, 3, 4, 5, 6, 7, 8. It owns 8. So its charge is negative 1. And this is our Lewis structure right here. So we have a central atom, and the last step is we want this central atom, since it's not chlorine or nitrogen, we want the expected to equal the owned. So that means we wouldn't have a charge in the central atom. That's kind of what's preferred. But we can't do that in this case because we have an extra electron and there's nowhere to put that electron. If we were to move these 2 electrons to make double bonds, because that's, if we want to move electrons, that's what we got to do. We got to make double or triple bonds. And we were to do this, chlorine would now have 7 around it, so it wouldn't be charged. But fluorine would now have 2, 4, 6, 8, 10. It would have 10 electrons in its valence shell, and that violates the Lewis theory here, Lewis structure theory. So we can't do that. We can't exceed octets in these periphery atoms. So this, unfortunately, we have to stick with this. This is the accepted Lewis structure right here for this theory. Again, your prof may prefer you to write it in the square brackets. 1, 2, 3, 4. Showing that the negative charge can be shared amongst. And in reality, this negative charge isn't strictly on the chlorine. It is shared amongst these atoms here due to the electronegativity of the fluorine. But anyways, this is what Lewis structure predicts here. Okay, for this next one here, OCS. Now oxygen, we see O is here. It's further to the right than carbon. It's higher than sulfur. It's more electronegative. So because of that, oxygen can't be the central atom. It's going to be carbon, which is furthest to the left and the least electronegative. So we're going to bond all the atoms to carbon here, and we want to add the number of valence electrons. Oxygen has 6. Here's oxygen. Count from the left. 1, 2, 3, 4, 5, 6. We get to 6. So there's 6, plus carbon has 4. If we look at the periodic table, here's carbon. Count from the left. 1, 2, 3, 4. And sulfur has 6 as well. So 6 is here right below oxygen. Count from the left. We'd get 6 to get to sulfur. Add that up. That's 16. There's 4 here, 2 from each bond. So we need to add another 12 electrons, and we add them first with the periphery atoms. 4, 5, 6, 7, 8, 9, 10. This now has a complete octet. There's 8 electrons around this oxygen here. We'll add another 6 to have a complete octet for this sulfur. There's 8 electrons around this sulfur, 6 here, and then 2 in these bonds, right? Every line represents 2 bonds. Rather than a line, you could write it as dots like this. It's also called Lewis dot structures. You may be used to seeing. Now, anyways, we have 16 electrons here. Now, in terms of the charge, oxygen has a charge of -1. We get that by doing the charge. Charge equals expected minus owned electrons. We expect there to be 6 for this oxygen. It owns 7. See, there's 1, 2, 3, 4, 5, 6, and then 1 electron in each bond is owned by each atom. So this electron is owned by this oxygen. This electron is owned by this carbon. Again, this is like fanciful this isn't in reality of what it is, but it's just a way of accounting, of keeping track of electrons, really, for this theory. So expected minus owned, 6 minus 7, so this is -1 as the charge. The carbon, we expect there to be 4 based on the periodic table. See, we have 4 here. It owns 2, 1 from each bond. So that means it has a charge of +2. And the sulfur, we expect there to be 6 based on the periodic table. And it owns 1, 2, 3, 4, 5, 6, 7. It owns 7, so its charge is -1. So now our last step is to deal with the central atom. And central atoms that are carbon or nitrogen, we want them to have a complete octet always. Well, pretty much always. You've seen the previous examples in this video where there might be an odd number of electrons and things. But anyways, we only have 4 electrons in this carbon's valence shell. 4 electrons associated with it. There needs to be 8. I'm going to turn these into lines because I like seeing them as lines better. Okay, so it's going to grab electrons from somewhere. Let's first grab the electrons from the sulfur. So I'll take these 2 electrons, and we're going to move them in between the carbon and the sulfur so they share these electrons. There we go. So now this carbon has 6 electrons around it, 2 from each bond. And get rid of the charges as well. It needs 8. And oxygen is the only atom that has an excess number of electrons. So we're going to take 2 electrons from the oxygen and make a double bond. And now carbon has a complete octet, 2 from each bond, so 8 total. And if we do the expected minus the owned for carbon, there's 6 expected for oxygen, 6 expected for oxygen. It owns 6, 4 non-bonding, and then 1 in each bond, so it's not charged. Carbon owns 1 electron in each bond, so it owns 4. We expect there to be 4, it's not charged. And then sulfur as well, it's not charged. Okay, so O3, ozone. So we have not really a central atom. I guess oxygen is its own central atom here. And we want to add the number of electrons. Oxygen, like we did in the last example, we expect there to be 6 electrons. So there's 6, and there's 3 of them. So 18 electrons. There's 4 here. We're going to add them to the periphery atoms to complete octets. So there's 6 here plus 2 in the bond, so this has a complete octet. And then we'll add another couple here, a few pairs here to have a complete octet. That's 16 electrons. We need to add another 2, so we'll add them to the central atom. Any remaining electrons get added to the central atom. Okay, now step 3, we need to determine the charge. Charge equals the expected minus the owned. And we expect oxygen to have 6 electrons. It owns 1, 2, 3, 4, 5, 6, plus 1 in the bond, 7. So it owns negative, so its charge is -1. That's these two outer ones. For this middle oxygen, we expect there to be 6. It owns these two, plus 1 in each bond, 4. So its charge is +2. And our next step is to complete octets, if possible. It's to deal with the central atom. So what we'll do is we have 6 electrons associated around it. So it needs another 2 electrons. So it's going to grab 2 electrons from one of these oxygens. So it'll take these 2 electrons, and to share it between them means to make a double bond. Okay, and there's now, so we did that. This oxygen now is a complete octet. There's 2 non-bonding, and then 6 bonding electrons. That's 8. This oxygen also has 8, so we have a complete octet here. And this charge, this oxygen's not charged. We expect our oxygen to have 6. It has 4 plus 1 from each bond, so that's 6, so 0. This one, we expect there to be 6. It owns 1 from each bond, that's 3, 4, 5. So that's charge is +1 here. And would we do this? Could we do this? Could we make a double bond here? Well, if we did that, we would violate the octet rule. And you can't do that with these second row central atom elements. I know I mentioned, I only picked on carbon and nitrogen when we did it, but oxygen is in the same boat. We can't violate the octet rule with oxygen. So this is our Lewis structure here. You could have had the single bond here and the double bond here. That would have been the same thing. Your prof may want you to write it in square brackets like this. Again, there's resonance structures, which we're not covering in this video, showing that the negative charge, there's no negative charge, showing that any charges are delocalized throughout the molecule here. All right, so next one here, we have this selenium dioxide molecule here, and we want to attach the atoms. Selenium is the central atom. If we look on our periodic table, selenium's down here. It's lower than oxygen, so it's less electronegative. It's also singular and written to the left. Next, we need to add the number of valence electrons. Well, selenium has 6 electrons, valence electrons. If you start from the left, 1, 2, skip the transition metals, 3, 4, 5, 6. So we have 6 plus 6 for oxygen. Oxygen's here, start from the left, 1, 2, 3, 4, 5, 6, and there's 2 of them. So that's 18 total. We'll start with the outer atoms to complete octets. 2, 3, 4, 5, 6. Now this oxygen has an octet because there's 8 electrons around it. 2, 4, 6, 8. We'll do the same for the other side. 2, 1 in each bond. 3, 4, 5, 6, 7, 8. There's 16 electrons here. We can't add any more to the oxygens because they have complete octets, so we need to add them to the central atom. So the remainder 2 ones go to the central atom, the selenium. Now we'll add the charges, so charge equals the expected minus the owned. We expect there to be 6 electrons on oxygen based on the periodic table. It owns 7, 1, 2, 3, 4, 5, 6, and then 1 in the bond is 7. So that's -1. Same thing, this oxygen would be -1. And then selenium, we expect there to be 6. It owns 1 from each bond, that's 2, plus these 2 here, so 4, so 2. So its charge is +2. Now, the central atom, we want, it's not carbon or nitrogen or oxygen, which rarely comes up, but I guess it's not that rare. It's above the second row, so we want the expected electrons to equal the owned electrons for any central atom in the third row or higher. Now here we have the expected not equaling the owned, it needs more electrons. It only owns 4. It needs 2 more. So it's going to grab those electrons from the oxygens. So we're going to take 2 electrons. I'll take these 2. And to move them onto the selenium, we'll create a double bond. That's what we do. To move electrons, we create double or triple bonds. And by doing that, this selenium now has 5 owned electrons. These 2 and 1 in each bond. There's 3 bonds, so 5. So plus 1. So it has a charge of plus 1. This is no longer charged, so it's 0. And here, so it needs another electron. So what we're going to do is, we can't take any more electrons from this oxygen because it doesn't have an excess amount of electrons. This one does. It's negatively charged. So we'll move 2 electrons over to make a double bond. And now the expected number of electrons equals the owned, 1, 2, 3, 4, because there's 1 in each bond. There's 4 bonds, 5, 6. So the expected equals the owned, so it's not charged. And same thing with this oxygen here. So that's our Lewis structure. Okay, for this one here, OCl2, this is a weird duck, right? Chlorine is less electronegative. So we would expect chlorine to be the central atom. And you may be able to write it as the central atom. But let's say where oxygen is the central atom here. It's singular and it's written to the left. We would attach the atoms like this. And according to the periodic table from the left, we count 1, 2, 3, 4, 5, 6. We expect there to be 6 electrons on oxygen, plus expect there to be 7 on chlorine. If we count from the left, 1, 2, 4, 5, 6, 7. And there's 2 of them, times 2. So 20 electrons, and we'll add them to complete octets first. 1, 2, 6, 1, 2, 3, 4, 5, 6. So this is, we have 16, 17, 18, 19, 20. And in this way, everybody has a complete octet. So we calculate the charge. The chlorine, we'd expect there to be 7. And there's 1, 2, 3, 4, 5, 6, plus 1 in the bond, 7. So there's no charge here. Same thing with this chlorine. Oxygen, we expect there to be 6 electrons based on the periodic table. It owns 1, 2, 3, 4, and then 1 in each bond, 6, so that's 0. So nobody's charged. So this is our Lewis structure here. You may want to put oxygen not in the center because it's less electronegative, and do something like this here. And let's see what would happen if we did that. So we have 20 electrons to add. There's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And if we do this, everybody has a complete octet, right? Everyone has a complete 1, 2, 3, 4, 5, 6, 7. This oxygen is negatively charged. That would be our next step. Step 3 is to calculate the charge. We expect there to be 6 on this oxygen. It actually has 7 because there's 6 non-bonding plus 1 in the bond. So 7 owned electrons, -1. This chlorine, we expect there to be 7, but it owns 8. 1, 2, 3, oh sorry, it owns 6, not 8. There we go. It completes the octet, but it doesn't have 8 owned. In terms of owned electrons, we only count 1 in each bond. Because like a bond is made up of 2 electrons. So you could rewrite these lines as like 2 electrons. And then 1 electron is owned by the chlorine and 1 is owned by the oxygen on both sides. So this chlorine owns 1, 2, 3, 4, 5, 6, plus 1 here. So we do have an octet, so this may seem to be a valid Lewis structure. I'm going to make these lines just because I feel more comfortable doing that. But how would we make this? Our last step for a central atom, it's not in the second row, it's not carbon and nitrogen. We want the owned to equal the expected, so this chlorine would need an extra electron. That means they would have to grab an electron from oxygen here. And if we do that, we're no longer charged. There we go. We have the expected equaling the owned on the chlorine, 7 equals 7. And same thing for this oxygen here, 7 equals 7. And both of these are valid Lewis structures. They're actually isomers of each other. So either one, if you're not given any other information, then you should be fine either way with this. Okay, next is H2SO4. So everyone probably knows this one, or most people anyways. Well, the trick though, I should say, if it starts with an H, the H goes to an O. So the central atom is sulfur. Sulfur is right here. It's lower down on the table than oxygen, so it's less electronegative. It's singular. So sulfur is our central atom. And if it starts with an H, the H goes to an O. So there's two H's, which means one H goes to one O and another H goes to another O. Doesn't matter which one you pick. Now we need to add up the number of electrons. There's one electron per hydrogen. See, one if we come from the left. Sulfur has 6. Here's sulfur, start from the left. 1, 2, 4, 5, 6. Same with oxygen, start from the left. 1, 2, 3, 4, 5, 6. So there's 1 for each hydrogen, plus there's 2 hydrogens, plus 6 for the sulfur, and then 6 for each oxygen, and times 4, because there's 4 oxygens. What's this? 24, 30, 32. 32 electrons. And we currently have 2, 4, 6, 8, 10, 12. We currently have 12. We need to add the remainder, starting at the outer atoms to complete octets. 14, 15, 16, 17, 18. This now has a complete octet. 19, 20, 21, 22, 23, 24. Now we have a complete octet. 25, 26, 27, 28. Complete octet, because there's 2 in each bond, plus these 4. I think I lost count, but this sounds right here. 8 times 1, 2, 8 times 3 is 24, 26, 28, 30, 32. Okay, so we have 32 here. Now we need to add the charges. So we want the expected to equal the owned. And for this oxygen here, we expect there to be 6 electrons. And charge equals expected minus owned. So expect is 6 based on the periodic table. We expect there to be 6. It owns 1, 2, 3, 4, 5, 6 plus 1 from the bond. It owns 7. So its charge is -1. Same thing with this oxygen. It would just be -1 as well. This oxygen here, we expect there to be 6. It owns 4 non-bonding and then 1 from each bond. 1, 2, 3, 4, 5, 6. 6 minus 6, so it's not charged. This one's not charged. And hydrogen can only have 1 bond, so it's not really ever charged. And then sulfur, we expect there to be 6 based on our periodic table. And how many does it own? It owns 1 from each bond. 1, 2, 3, 4. So plus 2. So this has a charge of plus 2. Okay, so now our last step, we want the central atom. Since it's not carbon or nitrogen, we want it to be expected electrons to equal the owned. So we want there to be, it wants to own 6 electrons. And we need more electrons. We need to put some electrons on the sulfur, and we're going to get those electrons from atoms that have an excess amount of electrons, these oxygens here. So since this has a excess amount of electrons, I'm going to take these two and move them to the sulfur by creating a double bond. And I'm going to do that with both of them. I'm going to save some time a little bit. And by doing that, this sulfur now has 6 owned electrons, 1 from each bond, 1, 2, 3, 4, 5, 6. So it's not charged anymore. And each oxygen still has a complete octet because there's 4 non-bonding and 4 bonding electrons. So there's 8 associated with it. So this is our structure here, H2SO4. Okay, xenon tetroxide. So for xenon tetroxide, we have the xenon in the center. Now it's further to the right than oxygen, but it's so far down, and these noble gases are always going to be central atoms. It's so far down they can support the most number of bonds, and it's less electronegative than oxygen. So xenon is our central atom. And we now need to add the number of electrons. Oh, I'm getting a little messy here. Okay, so xenon has 8 valence electrons. If we come from the periodic table here, From the left, we count 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8 to get to xenon. Oxygen has 6 if we count from the left, 1, 2, 3, 4, 5, 6. Plus 6, and there's 4 of them. So that makes 32 total. And we'll start with the periphery atoms, the outer atoms first to complete octets. So there's 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. This now has a complete octet. These 6 plus these 2 make an octet. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 8, 29, 30, 31. It's kind of hard to see that. 31, 32. I'll put them there. It's not the best spot, but it's easier to see. Okay. So we have 32. Now we got to calculate the charge, and the charge equals the expected minus the owned. We expect oxygen, based on the periodic table, we expect there to be 6. And this oxygen has 6 minus, how many does it own? It owns these 6 plus 1 from each bond, 7. So its charge is -1. That means all of these would have a charge of -1. And this is kind of where the theory breaks down. In reality, well, it's broken down a lot. It breaks down here in H2SO4. But we need to do the charge of the xenon. The charge is going to be +4 because we expect there to be 8. It owns 1 from each bond. It owns 4, so expected minus owned. 8 minus 4 is +4, so this has a charge of +4. So for our last step, the central atom, we want this expected number of electrons to equal the owned number of electrons. Since it's not in the second row, it's not carbon and nitrogen, expected should equal the owned. So it needs 4 more electrons to get 8 owned electrons, so that it's not charged. And it's going to grab those electrons from oxygen and just make things maybe a little bit shorter, if that's possible at this point. We're going to take a pair of electrons from each oxygen and make a double bond. By doing that, we're moving electrons towards this xenon, and we're going to do it with all of them. So I'll put those there, and over here I put those ones there, and I'll take these ones here. This should be an O, not a 6. Okay, by doing this, this xenon is no longer charged. It owns 1 electron in each bond, 1, 2, 3, 4, 5, 6, 7, 8. It owns 8. It's expected to have 8. 8 minus 8 is 0, so this is not charged. Each oxygen here has a complete octet, 4 bonding electrons plus 4 non-bonding electrons, and its expected minus owned is 0. We expect oxygen to have 6. It owns 4 and 1 from each bond, 5, 6. It owns, so 0, so each oxygen is no longer charged. So this is the accepted Lewis structure anyways, based on the Lewis theory of xenon tetroxide. Okay, for this next one, xenon's the central atom. It's written furthest to the left here. It's singular on the periodic table. It's not further to the right than the other ones, but it is a noble gas, and it's much further down. It can support the most number of bonds, and it is the least electronegative atom. So it's going to be the central atom, and then all the other atoms are going to be bonded to it. 2, 3, 4. Now, okay, so that's attach the atoms. Step 1. Step 2 is to add the electrons. Xenon has 8 valence electrons. Here's xenon here. If we count from the left, 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8. It has 8. Oxygen has 4, or no, oxygen. Fluorine has 7. If we count from the left, 1, 2, 4, 5, 6, 7. So fluorine has 7. Oh, and chlorine is right below fluorine. So if we count from the left, we'd get 7 as well. So we have 8 plus 7 times 2 plus 7 times 4, which is, I believe, 50. Okay, so there's 2, 4, 6, 8, 10. There's 12 here. And now we need to add electrons to complete octets, 13, 14, 15, 16, 17, 18. We have a complete octet here. There's 6 non-bonding electrons plus 2 bonding electrons makes 8. And then we'll add, oh, now I lost count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 40, 42, 44, 46, 48, and I believe that's 48. Oh yeah, because there's 8 for every outer atom. 6 plus these two, that's 8, and there's 1, 2, 3, 4, 5, 6 outer atoms. 6 times 8 is 48. Okay, so there's 2 more electrons to add. We can't add them to the outer atoms because they have a complete octet, so we got to add the remaining 2 to the central atom, 50 here. Now, we need to calculate the charges, and the charge is the expected minus the owned, right? Charge on the atom equals the expected number of electrons minus the owned number of electrons. Each of these outer atoms expects to have 7 electrons, right here, based on our periodic table, expect there to be 7. And each one owns, doesn't own 7. It 1, 2, 3, 4. Oh yeah, it owns 7. There's 6 non-bonding and then 1 electron in each bond. So 1, 2, 3, 4, 5, 6, 7. So this one owns 7, and they're all the same. So they all own 7. They're all expect to have 7 based on the periodic table. They all own 7, so there's no charge. What about the xenon? It's expected to have 8. And it owns 1 from each bond, 1, 2, 3, 4, 5, 6, plus the 2 non-bonding electrons, 8. So it's not charged either. So this is its Lewis structure, as big as it is, crazy as it looks. This is the accepted Lewis structure. Okay, Br2. It should be pretty obvious by now that bromine is the central atom, and we'll attach the fluorines to it. On the outside is the outer atoms. We'll count the number of electrons. Bromine is right here. Oh, here it is. I'm going blind. Holy. So we count from the left. 1, 2, skip the transition metals. 3, 4, 5, 6, 7. Bromine has 7, plus fluorine as well. Fluorine's right here. Count from the left. 1, 2, 3, 4, 5, 6, 7. And there's 5 of them. So that's 6 7s. There's 42 electrons total. We'll add them to the outer atoms to complete octets. 2, 4, 6, 8. So there's 10 electrons in these bonds, 2 from each bond. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. And we have a complete octet with each outer atom. We have 2 more electrons to add, so we've got to add those to the central atom. And in terms of the charge, just like with this one here, these fluorines aren't charged, so these fluorines aren't charged, and the charge is the expected minus the owned. We'll do that for the central atom. We expect there to be 7 with bromine, and it owns 1 from each bond, 1, 2, 3, 4, 5, and then these 2 non-bonding electrons, 7. So it's not charged either. So this is our accepted Lewis structure for Br2. Okay, for Cl, PCl5, the phosphorus is central. It's the least electronegative. It's further to the left here. Go to the periodic table. Here it is compared to chlorine. It's written to the left. It's singular. It supports the most number of bonds, well, in this case. So anyways, it fits the bill. It's the central atom. We need to add the number of electrons. Phosphorus is here if we count from the left. 1, 2, 3, 4, 5, we get to 5. Chlorine, we get 2 more if we count from the left, so it has 7. So there's 5 plus 7 for each chlorine. There's 5 chlorines. So there's 40 electrons total. And there's 2, 4, 6, 8, 10 electrons in these bonds, 2 electrons per bond. So 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, we've added octets to these outer atoms. See, there's 6 non-bonding, and then 2 electrons, 1 from in this bond. Each bond consists of 2 electrons, so each outer atom has 8 electrons associated with it in its valence shell, we say. So it has an octet, so that's good. And the expected number of electrons equals the owned. So the charge equals the expected minus the owned. If we look at this chlorine here, we expect there to be 7 electrons based on the periodic table, counting from the left. It owns these 6, 1, 2, 3, 4, 5, 6, and it owns 1 electron in this bond, right? This bond, think of this bond as being comprised of 2 electrons. 1 is owned by the chlorine and 1 is owned by the phosphorus. So it owns 7, so it's not charged. So none of these chlorines are charged. What about the phosphorus here? The phosphorus, we'd expect there to be 5, and it owns 1 from each bond. There's 5 bonds, so it's not charged as well. So this is our Lewis structure for PCl5. Okay, XeOF4. So xenon is going to be the central atom. It is further down here, but it's a noble gas, so it's the least electronegative. It's written singular, and it's furthest to the left the way it's written as well. So we're going to have xenon as the central atom, and then, I'll put the oxygen here, and the 4 fluorines around it. The outer atoms all attached to the central atom. I don't know why xenon looks bigger. It shouldn't be, but, well, it is actually, but yeah, okay. But, so next step, we want to add the number of electrons. So we go to the periodic table. Xenon has 8 electrons, 8 valence electrons, because if we count from the left, 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8. So there's 8 valence electrons. Oxygen has 6. Here's oxygen, count from the left, 1, 2, 3, 4, 5, 6, and then fluorine has 1 more, 7. So 7, and there's 4 fluorines. So this is 7 times 4 is 28, 32, 40. We also have 40 as well? Oh. Okay, well, that's cool. Anyways, we'll add those 40 starting with the outer atoms. So there's 2, 4, 6, 8, 10 electrons in these bonds because there's 2 electrons per bond. 12, 14, 16. We now have a complete octet with this fluorine. Octet means 8. And there's 6 here plus 2 in the bond. So this has 8. Now I lost count. 10. I think this is 16. Is that right? 2, 4, 6, 8, 16, 18, 20, 22, 24, 26, 28, 32, 34, 36, 38, 40. Okay, no extra electrons. Is that right? 2, 4, 6, 8, 10. Wait, so there's 8 in each outer atom. 1, 2, 3, 4, 5, 40. There's 40. Okay. 1, 2, 3, 4, 5. Okay. Did I make an error? Oh, aha. Okay, there's not, yeah, this doesn't seem right. There's not 40. I counted this wrong. What? Holy. Okay, so 8 plus 6 is 14. And 7 times 4 is 14, 28. So if we do 28 plus 14, 28 plus 14, so this is 12, carry the 1, 42. We need 2 more electrons. 2 more electrons. I had a feeling something wasn't going to work. And you know, if you did this wrong, as you go through, you would find out that you would not get a very nice Lewis structure. I kind of anticipated that ahead of time. Something was wrong. Okay, 42. So we can't add any more electrons to the outer atoms, so we add 2 to the central atom here. Now we find out the charge expected equals the owned. Now just like these chlorines, there's no charge on the fluorines here because they expect to have 7 and they own 7 for the same argument. And this oxygen is going to have a charge of -1 because we expect there to be 6. See right here from the periodic table. And how many does it own? It owns 4. This should be a negative, not an electron. 1, 2, 3, 4, 5, 6. Or it has 6 non-bonding electrons plus 1 in the bond is 7. So expected is 6 minus the owned is 7 equals -1. So a charge of -1. And then this xenon, we'd expect there to be 8 based on the periodic table. And it owns 1 from each bond, 1, 2, 3, 4, 5, plus these 2 non-bonding electrons, 5, so 7. So its charge is +1, +1. Okay, so for our last step, we want the central atom. Since it's not in the second row, it's not a carbon or a nitrogen specifically. We want the owned electrons to equal the expected electrons. So we expect there to be 8. We want it to own 8. It currently owns 7. So it needs an extra electron. It's going to grab that electron from oxygen because oxygen is negatively charged and it has an excess amount of electrons. So we're going to take 2 electrons, a lone pair, and make a double bond with xenon. So those 2 electrons that were here are now here in this line. A line represents 2 electrons. And by doing that, we've gotten rid of the charge, and we now have 8 owned electrons on this xenon. 1 from each bond, 1, 2, 3, 4, 5, 6, and these 2 here, 7, 8. And then this oxygen is not charged either. So this is our Lewis structure. Okay, now for our last set of 2 here. You're doing awesome. Thanks for hanging in there for so long with me. We're getting through this together. So we have SI6. Now, obviously, sulfur has to be the central atom. That's, I think, super obvious, and we could go through our criteria, but there we are. And then we have the outer atoms bonded to the central atom. And 1, 2, 3, 4, 5, 6. So 6. Now we need to add up the number of electrons. Sulfur has 6 electrons, valence electrons. Here's sulfur here, come from the left. 1, 2, 3, 4, 5, 6. So there's 6 here. Iodine has 7, because if we count from the left with iodine, 1, 2, skip the transition metals, 3, 4, 5, 6, 7. 7 times 6. There we go. So that's 8 times 6, so 48. We should have 48 electrons. There's 2 in each bond here. Each line represents 2 electrons as a bond that's shared between the 2 atoms. So there's 2, 4, 6, 8, 10, 12. We have 12 electrons. We need 48. We're going to add 12, 13, 14, 15, 16, 17, 18. Add them first to the outer atoms to complete octets. This iodine has a complete octet because it has 6 non-bonding plus 2 bonding electrons associated with it. So that makes 8. So we have a complete octet. 6, 8, 12, what, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, 18, 20, 22, 24. That's a complete octet. 26, 28, 30. That's a complete octet. 32, 34, 36. That's a complete octet. 38, 40, 42, 44, 46, 48. Whew. Okay, we got all 48 electrons on it. Now we need to calculate the charge, which is going to be really easy. Charge equals expected minus the owned. Remember, charge equals the expected number of electrons minus the owned number of electrons. So for this iodine, and for all the iodines, because they're all the same, we expect there to be 7 based on the periodic table. When we count from the left, we get to 7 to get to iodine. Skip the transition metals. So we expect there to be 7. How many does it own? Well, it owns 1, 2, 3, 4. It owns 6 plus 1 from the bond. See this bond? This bond represents 2 electrons that's shared between the 2 atoms. And in terms of housekeeping, this isn't in reality, but in terms of our housekeeping, 1 electron is owned by the sulfur, the other electron's owned by the iodine. So there's 1, 2, 3, 4, 5, 6, 7 owned. So it has no charge. And then same thing, all these other iodines are the same, so they'd have no charge. And this sulfur as well, we expect there to be 6 on this sulfur, 6 valence electrons, and it owns 1 electron in each bond, 1, 2, 3, 4, 5, 6, 6 minus 6, so it's not charged as well. This is the Lewis structure here. Does it actually look like this? Well, there's kind of more to the story, but in terms of the Lewis theory, Lewis structure of this compound, this would be acceptable in general chemistry. Okay, so now we have IF6, and same thing, iodine has to be the central atom, and we'll put the 6 fluorines around it, 4, 5, 6, and okay, so that's it, central atom, and then attach the outer atoms to the central atom. Now we need to add the electrons. Iodine is here, count from the left, 1, 2, skip the transition metals, 3, 4, 5, 6, 7. So iodine has 7, fluorine has 7 as well. If fluorine's here, count from the left, we get 7 to get the fluorine. And there's 6 of them. And now now we're positively charged, so we need to subtract an electron. Because let's say it had 7 plus 7 times 6, right? If it had this many electrons, it would not be charged. But for it to be positively charged, it has to have 1 less electron, because electrons are negative. If you lose a negative charge, this thing's now positive. Okay, so we have 6 times 7 is 42, plus another 7 is 49, minus 1 is 48. And we're going to add those electrons first to the outer atoms to form octets. And I'm just going to add them all to complete octets, just like what we did last time, just to make it quick. And, okay, and how many electrons did I add? Well, there's 8 with each atom, because we have an octet which with each other atom. There's 6 atoms, so 8 times 6 is 48. Okay, so we're good, 48. Now we need to know the charge. Well, if we look at fluorine, charge equals expected minus owned, and this is true for these fluorines. So we expect what I wrote for the iodine is the same for the fluorine here, because we expect fluorine to have 7, so it's 7 minus how much does each fluorine own? How many electrons does each fluorine own? It owns 6 here, plus 1 from each bond, so 7. So there's no charge on the fluorine. What about the iodine? Well, the iodine, we expect there to be 6 based on the periodic table, and it owns 1 from each bond. 1, 2, 3, 4, 5, 6. It owns 6, so it's positively charged. So we'll put the positive charge on the iodine, and this would be our Lewis structure here. Now, your prof might like to see you write it like this with square brackets, depending on their preference. 1, 2, 3, 4, 5, 6. It's kind of a lousy F. There we go. Don't forget all the electrons around. They're all worth marks. In square brackets here with the positive charge as a superscript. Alrighty, my friends, we just went through a huge number of Lewis structures, and if you can follow this and go through it, I hope it's getting repetitive. I hope you start seeing the pattern and how this method is super solid and how you can get the right method every time. If you got some value from this, spent a lot of time putting it together. I really hope you did. I really hope you enjoyed it, and it's going to help you in your chemistry course. And if it did, and if you think it's helpful, consider liking it or maybe even subscribing. Thank you again, and good luck in your course. Cheers.